everyone, remember a couple things. Remember that for translational motion, we have two major equations. We have the sum of the forces in the x direction equal ma in the x direction, and we have the sum of the forces in the y direction equal ma in the y direction. Now, sometimes we will adjust this. Hey, hold down, please. Sometimes we will adjust this, and we won't write it x and y because x and y is not convenient. When is it not convenient to do x and y as our coordinate system? And when our acceleration is not either in the x or the y, right? Okay, now remember that if we have a single acceleration that we can deal with, then we try to set up our coordinate system so that it's like this. So the sum of the forces in the parallel direction, the sum of the forces in the perpendicular, perpendicular.
It's still perpendicular.
Upside down. It is perpendicular. In the perpendicular direction equals 0, A, which is 0, and this is MA parallel, which is just this, okay? So that makes life simpler on us, right? So we try to make it so that in one direction the acceleration is always 0. Now there may be an occasion or two where we have an object like this going around in a circle. It's moving this way, and it's moving in a circle, and it's a vertical circle, and it's not a Ferris wheel, so it's not keeping a constant speed. So it's like a ball on the end of a string or something, okay? Or a roller coaster car or something. Okay, in this case, there's going to be a force down, mg, and a tension this way. It's moving out in this direction. Velocity is this way. All right, in a case like this, where we have more than one type of acceleration, we have both tangential and centripetal, thank you. Then what we need to do is set up our coordinate system so that it's like this. Our coordinate system will line up like this. One towards the center and one parallel to the velocity. Or you could say one radial and one tangential if you want. Okay? One perpendicular to the path, one parallel to the path. Okay? Because in this direction, the radial direction, the sum of the forces equals ma, but that's our centripetal direction, right? So our acceleration here will be v squared over r. And in this direction, the sum of the forces equals ma. That's going to be our acceleration that just is speeding up or slowing down, right? Does that make sense? All right, so we'll end up with 2F equals ma's, but at least we'll be able to figure out what the two a's are, what the two accelerations are, right? Okay. So when we have translational motion, we have two perpendicular directions where we consider our acceleration because it helps us figure the vectors out. If our acceleration is not in x and y, we do this. We tilt our axis to make math simpler. And if we have both radial and tangential, or centripetal and parallel, whichever one you want to call them, then we split it up in those ways, and we have 2F equal ma, one of them being centripetal. Okay? One changes speed, one changes direction. All right? That just helps us out mathematically. It's a simplified, or it's a systematic way of going about handling the problem so that you make sense of it. All right? Okay, but then we have objects that rotate. Okay? The object itself, where it's not translating x or y or any direction necessarily, but it's rotating about an axis. Okay? Now in those problems, when we draw our free body diagram, it's dreadfully important that we draw our free body diagram correctly. Now, the forces are located where they are on the object. Okay? Because remember, the torque makes all the difference in the world whether it's going to rotate. And what's torque again?
R cross F.
R cross F. Or that's called
RF sine theta.
RF sine theta. Or that's called
R sine theta.
or it's called
Negative F cross
RF perpendicular, where the force perpendicular to the radius. Or it's called are perpendicular to the force.
That's a lot of things for one day.
That's it. That's all I got. Let me draw it again. Here's our wrench. Here's our radius to our force. I'm going to draw my force down this way. Okay? Technically, that's our angle theta, because the radius is going out that way, radius cross F. So which way is our torque vector pointing? And don't say this way. It's going that way. Yes, and then remember, we don't want curvy vectors because then our triangles look really weird when we try to add them. Right? A plus B equals A squared plus B squared equals C squared.
I think you made it.
Yeah, exactly. I'm confused.
Okay.
All right. Okay, they have to be straight. The only way to make a straight arrow for something that's rotating is to draw the arrow along the axis. So we have two ways of drawing it along the axis. Either this way or this way. I'm sorry.
Stop it.
Which way is it?
Right.
Right hand rule. So which way is the torque vector pointing? R cross F. R's going that way, F's going this way, so it's R cross F. Into the board. So our torque vector,
I didn't know this looked like a right. This right hand is recorded?
there's our torque
What he was
vector.
doing last time.
Into the board.
He spent like a long time on it. I was confused. See the R?
R. Okay, must do this. R cross F.
Cross F. I'm gonna be doing this on the test.
Yes, you will. And you must. Because the very first few times you do this, it's very few people can visualize this in their brain the first time. And even after much practice, those of you that are not visual learners, those of you that are visually impaired, okay, will not still be able to do this without some physical helper. Okay, so this is your helper. You need something? Talk to the seniors, come on in. Oh, Mark Sears. Others said talk to the seniors. Come on. Excuse me. So there we go. R cross F. R cross F. R cross F. All right? You must look stupid. If you don't look stupid, you probably won't get it right. But you're among other friends that also look stupid, so it's okay. All right? So, now remember, here we go. R cross F, or RF sine theta. But remember, that's the same thing as the perpendicular part of the force. So like if your force is this way, then the perpendicular part of your force is all that's causing you to have torque. The parallel part of your force is not causing any torque. So no torque, torque. Okay?
So that would be turning the wrench and pulling it off.
Yes. So this would be torquing the wrench, causing it to try to making it turn, and this would be pulling the wrench off. So if you did that, you probably wouldn't do very well.
Wait, what?
Okay? See, this force is causing the wrench to come off. This force is causing it to try to rotate, creating a torque. Okay? So only the perpendicular part.
What if you weren't pulling the wrench, but you
You,
Make sure it's
then it would be facing
You wouldn't
that
do
way.
that.
No, it wouldn't.
you might.
It would be facing that way.
Here's your force.
No, but what if no, like in the same direction that you were pushing. So
That's not-
technically it would be shifted up above.
You wouldn't do that like I did. That doesn't make any sense.
I don't know.
Draw it the way
Can you draw it back the other
you had
way?
it before.
That means a pull, okay? Pushing on the left side.
Whether I do this
No, but the
or
arrow.
I do this, it's the same thing.
No, but the arrow's on top.
It doesn't matter. You're still pulling the wrench off.
A pulling force is the same as
Here, come up here, and I will twist your arm one way by pushing, or twist it the same way by pulling. And I bet I can knock it out of socket both ways.
That's lovely.
All right? Yeah, do it. Yeah, that's
In the name of physics.
right. In the name of physics, we
She's a
need
martyr.
to torque your arm out of socket. Okay, now, here's the other thing. What if you were pushing this way with a force?
Righty tighty, lefty loose.
Righty-tighty, thank you.
Traded in for what?
Okay, this would be the exact same as if your wrench was over here. Wrench. Can you see this?
The wrench turned and got swung.
Imagine.
Now look,
The radius.
It got shorter.
That's exactly.
That's what happens when torque.
okay,
That's what we focus on.
the wrench changed colors. Okay, that's not the physics of what's
It
going on.
did. No.
That's chemistry.
All right, focus, focus, focus. All right, here we go. If I had the blue wrench and I applied a force right here on the blue wrench, that would be equivalent to using the black wrench with the same force if I applied it like that.
Is that black line supposed to be straight?
Yeah, that's straight. Can't you see? Come on, it's straight. You're just looking at it. Look like this.
You made it worse.
And it's called straight.
Worse when you go like that.
That's right, the
It's a
force-
parabola when you squeeze into
Oh, it's
it.
not right. All right, look.
Okay, can you repeat what you just said?
Okay, the deal is this. If I had this blue wrench and I applied a force like this at an angle, is all of my force being effective at causing it to rotate? No. Not very good at trying to make a torque. Okay, so I have two options. I could either say, look, just this perpendicular part of the force is causing torque. So I could just use this perpendicular part of the force times this radius, and that would be my torque, right?
Yes.
But mathematically, that's exactly the same as if I use this entire force just on a smaller radius, right?
Wait, why?
Oh, because it's the perpendicular.
Because I could rewrite this equation r sine theta f.
Oh,
This is f perpendicular, and this is radius perpendicular to the force.
Right, but you have to. So you make that perpendicular angle between the entire force and the radius. What are you talking about?
Yes, the entire force
And then you make a perpendicular angle.
and perpendicular radius. Okay,
Okay.
let me give you another example. What if you had an object like this that was circular, okay? And let's say that you applied a force right here, okay?
Okay.
All right? And here's my radius. Okay?
Yes.
If I apply this force right here instead,
How do you apply it right there?
I just
You just
Magic.
extend it.
do.
There's a handle.
Is an object like a Ferris wheel type
the
of thing?
same.
Or like you have
I
like
get the exact same torque. If I apply the force here instead of here at a shorter radius. Now how can I get the same torque here that I get here?
More this way. Make it more perpendicular.
Bigger S.
Because while I have a shorter radius, it's now a perpendicular force, so the force is more effective at producing a torque, right?
Or the angle has gone to.
Yes, or my angle here has gone to 90, which increases my torque, even though the radius has gone down. In fact, if I apply this force anywhere along this line, I'll get the exact same torque. Identically the same torque.
It's the same.
But then you just say it would. That's very
But
interesting.
before, it's the same torque.
If it's
That's
if I
the
play
force is different.
if I play force, it's the same force.
All right? You don't believe me?
No, I
It's the radius change.
You don't.
So the angle is
Real life
it makes the
The
Perpendicular.
effective torque increases, but the radius is decreasing.
that line. Oh, yeah.
Yes?
Then the torque in general is increasing?
The torque is the same. Because what's happening is torque equals RF sine theta. Sine theta is getting larger as the radius gets smaller. These two are exactly balanced. So the torque remains the same.
So it stays the same.
Do you want to solve it mathematically to prove it? I can. Do you want to?
Yeah, just do it.
All right, here we go. We're going to go for it.
We're not paying attention anyways.
I just had to go over. I had the cord. I had to shut it.
Okay, here you go. Okay, this is 4 meters by 2 meters. You're going to apply your force right here at 3 meters up. Okay? Let's say your force is going to be, I don't know, 10 newtons. You're going to tip this thing over. Okay? You're going to tip this thing over. It's a box. You're going to push on it. You're going to push on it right here with 10 newtons. It's a big box. And you're quite tall. All right? And what I want you to do is, there's a couple things going on. I just want you to figure out, real simply, is how much torque are you producing? Now this thing is going to have other forces acting on it. This is not the only force. There's going to be right here, from its center of gravity, a weight, mg. There's also going to be a normal force and friction. If you're going to tip something over, there has to be friction, otherwise it'll just slide. Okay? Friction will be along this line of action. And the normal force, when you tip something over, where will the normal force be located? At this point, right here. Okay? So the deal is this, is that friction and the normal force are going to be at the pivot point. So you're going to have two competing torques trying to keep this thing from being tipped over, and the force trying to tip it over. So the torque from this force tries to tip it this way, about the pivot point. The weight of the object tries to keep it from being tipped over. And these two play no part in the tipping except to keep it from falling through the floor and to keep it from sliding along the floor. But don't cause any torque.
But eventually doesn't mg act as another torque force?
mg is a force that causes torque.
But
That causes it to fall.
Ah, yes. Now if you get the mg up to right here and a little bit past, oh yeah, then it'll cause the torque over with you and then you've won. Right? Okay, when it's in this situation right here, here's what I want everyone to do. Everyone. I want you to figure out, using the equation, torque equals R cross F, which is RF sine theta. How much torque do I get from the 10 newtons? Now remember, our radius is right here. This is our radius. And remember that if that is our radius, remember it's pointing this way. That's the direction of my radius. This is the direction of my force. And so where is my angle theta technically? Technically it's right here. Now if you're going to use your math and be smart about it, the sine of that angle is also equal to the sine of what angle?
The angle underneath.
Yeah, either this one or this one, right? They're the same?
Yes.
Remember, because of the symmetry of sine,
Yes.
the sine of two supplementary angles is the same, right? So you could also use this one, which is the real theta, in our equation. Or you could use either this one or this one. Okay? Either one of those two will also work. But there you go. Would you please figure out,
So it doesn't matter.
Wait.
I want you to figure out, it doesn't matter which one you use, because the sine of theta and the sine of 180 minus theta is the same number. Okay? So this is theta, this is theta 180 minus theta, and this is also 180 minus theta. So you could use one of those angles, which is what most students will do because it seems simpler to them.
Which theta?
It doesn't matter.
You have to figure out what theta
Any
is.
of those.
You use any of the angles at all.
Yeah.
Well, you,
Any of those four.
actually, any of this one, or this one, but not that one or that one.
So what are we looking
Not the little one. Just
don't
stop.
don't
Just
take this
stop.
one. No. No. All right.
No.
These guys.
R. Okay.
R is at 5.
Oscar, something to 80.
R is.
So this is emergency announcement. If Midge Carey is in the building, please call the health office. Midge Carey, you need to call the health office, 5130. Thank you.
3.6?
That's no good because that changes my angle. Oh, that's right. I didn't make my 3, 4, 5, did I? I made it 2, 3, square root of 13.
Did you say what is this object exactly? Because it's ginormous.
What are you doing? I'm working here.
I got a negative answer.
You got a negative answer. Are you in radiant mode, young man?
Why, thank you.
No, I did that wrong.
Oh, that makes sense.
After I got that whole sign thing. You did 25.
Okay, I'm good.
Hey, has anything?
All right. What do we get?
30.
I got 29.9. Wait a minute, 30. You're wrong. 30 what? 30 hogheads?
Newton meters.
Newton meters.
For a long
Oh, I got 30 also. Awesome.
Newton meters or meter newtons?
Doesn't matter.
Meter Newton.
Mr. Ruin, why did we go through all of that?
Okay, because somebody didn't believe me. So I had to prove my intelligence, which sometimes is necessary. All right, so here we go. Here's the equation, r cross f. That's rf sine theta. Radius was square root of 13. Force was 10. Angle was 124, or you could have used this 156, right?
Yeah.
Did you still have to do sine or?
And you get,
Yes, you said.
yeah, still have to use sine.
If you don't round, you get exactly.
Yeah, and if I didn't round, this would be 30, right? Now,
Hold on.
let's solve it a different way. Let's go torque equals R F perpendicular.
You mean
No, RF perpendicular. Look. Look. All right, right here. I want to find the perpendicular part of this force to this radius. That would be right here. So here's my triangle. Uh-oh. Help me out here. See this angle right here, which I will call frowny face because this requires geometry and most of you have forgotten yours. Well, how big is that angle?
We don't know.
Yeah, figure it out. You got 10 seconds.
Half of
90 minus 56.
Okay.
Yes.
Oh.
Because this is 56.
Oh.
This is perpendicular. So this is 90 minus 56. So angle frowny face is, what is it? 34 degrees. Now, how do I find the perpendicular part of the force? You would probably go F perpendicular equals F cosine of 34 degrees. Now, I'm doing this on purpose, everybody, using cosine. Because if you realize that torque equals R times the perpendicular part of the force, sometimes the angle they give you is not the correct angle in the problem. And you need to be careful about what angle you're using. And you need to be aware of what you're trying to find. What you're trying to find is the perpendicular part of the force to the radius. And for us, that's going to be 10, radius, is square root of 13 times 10 times the cosine of 34 degrees. Okay, what's that turn out to be?
30.
It better be 30. Okay, if you don't believe that, then go torque equals R perpendicular to the force. That's the minimum radius to the force line of action. So where's the line of action for the force? That's this right here. There's my line of action to the force. Where's the minimum radius? Or what is the minimum radius? How long is it?
3 meters.
It's right here. 3 meters is the perpendicular radius. The radius from the pivot point perpendicular to that line of action. Okay. What's the minimum or perpendicular minimum radius?
3 meters.
3 meters. What's the force?
10 newtons.
10 newtons. What's our torque? 30. Okay, which one's easiest?
The R perpendicular.
This one. Now this will not always be the easiest. But sometimes in the problem you can pick the minimum perpendicular radius right out of the problem. And when you can find the minimum perpendicular radius right out of the problem, then you use this one. If it's easier for you to find the perpendicular part of the force to find the torque, then you use this one. And if neither of these looks convenient, then you got to go back and do some work, right? But all of these must give the exact same answer. Okay, mathematically they'll give the same answer every time. Okay? Now, did that help? Okay. So, along that line of action, now this is going to be really important because we're going to use this again when we get to angular momentum. In angular momentum, I think I talked about this last time, is as a car goes past, as a MV, as a momentum, as a car goes past a point right here, it has an angular momentum. Angular momentum, here you go, L, is equal to R cross MV. Okay? But wait a minute, that looks awful familiar. R cross something. That's a vector, right? Which means that as this thing goes past this point, then couldn't we just do this?
It's going to be the same.
And find our perpendicular radius and multiply it by my MV, and then we've got our angular momentum, right?
Could I ever?
Could I ever? Exactly. So there you go. Now, we're not solving this right now today. I just want to let you know that this is going to reappear, this minimum radius, okay?
That's what angular momentum is.
Yeah, angular momentum actually is I omega, but it's also that. It's one of two things, depending on whether the object has a lumpy mass shape, which means it has little discrete pieces of mass, or whether it's a continuous object. If it's a continuous object, it's going to be this. We haven't talked about what moment of inertia is yet, so that's why I didn't give you that one. But this one we could do. That's right, lumpy mass.
How do you get R?
Okay, so that brings us to that.
No, we'll do that later.
What? Oh, angular momentum? Yeah, I'm just showing you that it's going to reappear. You don't have to know that yet.
Yeah.
I don't expect you to know that yet. You don't need to know that yet. Okay, that brings me back to the orange sheet of paper. Orange.
Oh, that's what we started with, isn't it?
Yes. Where your force is located makes a huge bit of difference to what your torque's going to be. So let's draw our free body diagrams. So, let me just start calling off random names.
I'm like, okay, I'm still 25. Right there, 30.
So do we all have 8 people?
Yes.
Yeah.
What was that? So we could get rid of 7 people and still have 8 people
No,
for top.
no, because I'll not be top 25. I need this top 25.
But your number will go up to, like, I don't know. What is it?
I say 7.
Yeah, the
right?
ninth person is at 10.3%.
25 minus 7.
Sorry.
Oh wow, I'm barely
Top
in
like
my
where?
All right. What are you doing?
Yeah, if you
Calculating your net worth. Let's look at number 1 as a guideline. Here's the first one. The first one has this meter long, or it has 10 markings on it, this beam.
I'm gonna say it's 10.
The beam itself, 10 meters, I don't care. The beam itself has a mass, so it has a weight. It's uniform, so its weight is concentrated as if it's in the center. Okay, we're going to talk about center of mass a little bit later, okay? But for now, just like last year, we're going to assume its weight is all concentrated in the center, and the weight comes straight down from there. It has two sacks tied to the end, 2W here, and has a tension here that's perpendicular. All right, now, here's the thing that's important for us at the moment, is that in order for this to be an equilibrium, these three things must be true. The sum of the forces in the x direction must equal 0. The sum of the forces in the y direction must equal 0. And the sum of the torques must equal 0. Now when I say equilibrium, that means it's either at rest and staying at rest, or it is moving at a constant speed and could be rotating at a constant speed. So we could have an object that is at rest but rotating at a constant angular velocity. That's an equilibrium. Or we could have an object that is moving like this at a constant speed, velocity, but not rotating. Or it could be rotating and moving at a constant speed. That's also an equilibrium.
Mr. Aaron, I guess equilibrium cannot be defined as zero acceleration.
Or you could just say equilibrium is when your translational and rotational accelerations are both 0. No alpha, no A. All right? Does that make sense? Okay. So here's the deal, everyone. For this to be an equilibrium, which way does the force here at the hinge have to be? Why to the right? Okay, this one's just down, this one's just down, this one is both up and to the left. So therefore, you've got to have something here to the right. Now they're breaking this reaction force, which is technically a normal force, probably. They're breaking it down into horizontal and vertical components. So there's the horizontal component. We know we have to have a horizontal component to the right because the tension is pulling it to the left. Okay? All right, now, what about the vertical? Does the vertical have to be up or down?
It has to be.
Well, if the tension is big enough, then it could be done. Just
It's possible, right? Now there will be some situations where it's going to be very hard for us to tell which it is, okay? Whether it's going to be up or down. And in those cases, you can still list it mathematically what it's going to be. And then if you drew it in the wrong direction, your answer will just turn out to be negative. That happened all the time in engineering. All right, if this one is up, what's it going to have to be equal to?
3W.
minus
These three down
minus T
minus this vertical part up, right? Okay. All right, so there we go. So let's look at the rest of these. Some of these are going to be harder, and some of these are going to be easier. But remember our three equations, because all of these are in static equilibrium. Okay? You'll take an entire semester in college on statics. In statics, you'll do nothing but make sure the object's not moving. And these will be your three primary equations for the entire course. And you're thinking, wahoo, how easy can it be? But you just wait. Here's number 3. In number 3, we have a weight on the left and a weight on the right. And these two weights are evenly distributed as far as their distance from the center pivot point. Okay? Now, all right, I got a question on this one. As far as the bar goes, we're interested in forces on the bar. Then, if we're talking about forces on the bar, then there's weight on the bar, or force down from this object, and a force down over here. But the normal force comes from the bar on the sides, right? So those aren't there. Okay? There's no force up. Okay? Because that's the force on the sack itself. The sack is right here, and then there's a normal force up on it, right? So on the bar itself, there's just this force downward, which is equivalent to the weight. Weight, 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 and this one up is going to equal what? 3W. There we go. Is there a need for a horizontal force here? Wake up.
No.
Okay.
Why do you still need the vertical up if the 2 weights on the side cancel.
All right, excellent point, everybody. The question was, if this is the pivot point, and the torque from this one and the torque from this one cancel, and is there torque from this one right here? No, because it has no radius, right? Then why is there a need for this center force?
That's radius work.
Okay, because this one over here and this one over here is satisfied torque equals 0. But I have this one, and this one down, and so that's going to want to accelerate down, so therefore I need a force up to keep it from accelerating down. Right? Okay, here we go. Where's number 4? Here's number 4. Number 4 is right here. Okay, once again, no normal forces. We're looking at the forces on the bar. Okay, just draw the bar itself. So we have 2W down here. We have W here. We have an mg or a W here. And that's our pivot point. So, in order to satisfy the x direction, do we have equilibrium in the x direction already?
Yeah.
Sure, there's no force in the x direction, so we have equilibrium. Do we have equilibrium in the y direction? No, what do we need to make equilibrium in the y direction? 1, 2, 3, 4W up, which is going to be right here at the pivot point. So we have a 4W up. All right, do we have equilibrium in torque? Okay, here's our pivot point right here. What's my torque from this one?
2 times 2, 4.
All right.
4.
Now remember, I'd like for you to remember when you think of your torques, think radius first and then force, just so that we're doing it in the direction, we're doing it in the order of the cross product, okay? That way you also don't forget your radius. So 2 times 2W, which is 4W. 4W this way, right? Counterclockwise. Okay, what do we have over here? 1, 2, 3, 4W this way. So we're in equilibrium, right? Good shape. Okay, over here.
Yeah, the W is supposed to be 1 more to the right.
Is it?
Yeah, I can't count.
1, 2, 3, 4. No, it's right. 1, 2. Yeah, you got it right.
No, for the black.
Oh, this one.
Yeah.
This one?
One on the left.
1, 2, 3, 4.
It's supposed to be 1 more to the right.
It's
1,
just supposed to
2,
be
3.
3.
Yeah.
Oh, it's only supposed to be 3.
I know, right?
Otherwise.
Rammed up against the thing.
Okay. All right, so here we go. X equilibrium, it's all done. Okay, Y equilibrium. 3W plus 1W. The normal force up needs to be 4W. Good, good, and good. All right, torque on this side is 1 times 3W. So it's going to be 3W torque this way. And this one's going to be 1, 2, 3 times 1W, or 3W this way. So the torques cancel out. We're in equilibrium, right?
Everybody.
All right, and everyone's happy. Okay, this one. All right. Okay, when you draw your free body diagram, just draw the bar itself. That's all you need. All right, so we have a tension here.
Yeah,
Mr. Bruin, why on that one we didn't have a weight going
Yeah,
down?
like on 4 we have a weight going down where the little triangle thing is.
At the pivot point.
Yeah, pivot point, but on the black one we don't. And it's just 4W.
Ah, good question. In, let's do this in blue. No, let's do this in black because nobody wrote with black. In each one of these, we will do the weight of the object itself. Here. 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 And here.
We don't have.
We don't have one at the pivot point this time because all the rest of them had the bar at the pivot point. Here.
Because the weight is going to be...
See, this object right here has a force straight down. Its weight as if it's right here, straight down. In all of them up to number 5, the pivot point is right here. Okay?
Where the weight is.
In number 5, it's right here. So that one is still exactly where it's been before. It's just not at the pivot point this time. Does that make sense? All right. Excellent. All right.
Marker?
Lost it for a second. Okay, here we go. This one right here. Here's our center of mass. Here's our weight right there. Okay, we've got a tension over here. Tension. Okay, do we need a horizontal force at the pivot point here? We need a vertical force, but is our vertical force up or down? Okay, it seems to make sense that it would be up. Let's make sure. Okay? Now, this is a cool little trick that I taught you last year. It is that when something is in rotational equilibrium, that means it's not rotating about any point, right? If it's not rotating about any point, that means you can pick any point to be your pivot point.
And then it won't move.
And it won't move about any point whatsoever. So therefore you can pick any point that's convenient as long as it's in rotational equilibrium. So if you pick this center point as the pivot point, say I make this my pivot point, then this is going to torque it this way. So therefore I need a torque this way to keep it from rotating, right? So there you go. And in fact, since this is in the middle, then that tells me that since this radius and this radius are the same, therefore these two forces have to be the same, right? Because torque equals R cross F, where F over here is T, and torque over here equals R cross V. These have the exact same radius, so therefore T and V must be exactly the same. Does that make sense?
Yes.
All right. So there we go. So let's turn the page over to something a little bit more strenuous. Okay, number 7. Okay, right here at the center of mass, we have an mg. I'm going to call him mg, or you can call him W. Would you rather me call him W? Is that?
W.
I'll call him W because that's what the paper asks for.
MG makes more sense.
It asks for W in the direction.
No. W.
They're all the same.
I know, I want to write mg all the time. But this will work. Okay, we have a tension this way. We know that for sure. Okay, so what do we have going on here at the wall?
Horizontal.
Horizontal which way?
Left.
Why?
Because it's equal to the right.
Because we've got this and we got this. And so we need to have this horizontal to balance that. Now, how about vertical?
I don't know because the W is going down, so I don't know.
Minus
Because that was going up and then.
minus the Y component.
No, it's not balanced as is. And here's why. Because if I pick my pivot point to be here, it's going to torque this way, right?
So you need
If I pick my
vertical
pivot
up.
point here, it's going to torque this way. So something's wrong.
You need vertical.
So what if I pick my pivot point at the wall?
If you pick your pivot point at the wall, Mr. Smarty
I'm
Pants,
just wondering if it is.
here's the reason why that won't work.
If you cut the tension, then it will.
Here's why it won't work. If you pick your pivot point at the wall and you argue that, well, this is going to torque me clockwise, that's going to torque me counterclockwise, so won't it all be good? But we know from this equation right here that the down must equal the up. And so if that's W up,
Distance, okay, cool.
will it be in rotational equilibrium?
No, because the radius is.
Ah, if this is W and this is W and here's my pivot point right here,
Fail.
that's going to produce a lot more torque than this one because it's twice the radius, right? So that won't work.
Okay, that makes sense.
So we got to get rid of that. Let's pick a pivot point that helps us out. Why don't we pick, you want to pick this as your pivot point?
Yeah.
You pick that as your pivot point, then that means we have torque from this force right here around this way.
So that equals.
So that means that this has got to give me a torque which way?
Up.
This way. So I must have a vertical force up. And once again, this one and this one must be the same because they have the same radius. They must cancel each other torque-wise. So they must be equal. So here, question for you. You ready?
Yes.
Why doesn't this horizontal force produce torque?
Because it's
So it's
the
Okay,
angle
it's
between
parallel.
it is
It's parallel to
zero,
the thing.
right?
What's its perpendicular minimum radius?
0.
Do you see it? It's 0. Because its line of action passes through the radius, through the rotation point. So it has no torque for the pivot point I picked. Okay, that's why I can neglect it when I talk about the torques. Okay?
I'm kind of confused. You don't have to have anything to balance the W.
Yes, I got a bunch of stuff that balances the W. In fact, let's go through the math, because this is a good point to start showing this. All right, the sum of the forces in the X equals 0. Therefore, I have a W down, which must equal the T vertical up plus the vertical.
This is ruining.
Ah! I didn't why. In the X direction, I must have a horizontal balancing out my T in the, I'm just going to say the X direction. Is that easier? There you go. In the Y direction, then my vertical up plus my T in the Y direction must equal W down. And for my torques, you can make any torque equation you want from any one of these, any pivot points you wish. But there are 3 convenient spots to pick the pivot point. You can pick the pivot point here, or here, or here. And why are those 3 convenient? Because it eliminates some of them from causing a torque, right? In fact, what some of you might want to consider is this. You might want to consider this as your pivot point right here, because it eliminates this one with the angle. And it also eliminates this one. And so the torque then would be the torque from W must balance the torque from V. So which one is a bigger force, W or V?
V. No, wait, W. Wait.
They're equal.
They're equal.
Very good, because this one has twice the radius of this one. So that means W must be twice as big as V. Okay, very nice. And since V equals this part right here, the vertical part of T here and V here are going to be half the weight. Okay? See how that works? All right, piece of cake. Let's go to number 8. Number 8's actually easier probably. You've got an mg somewhere over here, or a weight. I'm going to do mg, I can't stand it.
Thank you.
Can't stand it. All right. And at 1, 2 1/2, we have a tension here. And at 1, 2, 3, 4, 5, we have a tension here. Are these 2 tensions the same?
No.
Oh, no. Which one's bigger?
Right.
Okay, but I do know that tension 1 and tension 2 must equal mg.
In the
Correct?
right direction.
I get this equation from my y. Now, torque. Let's figure out the torque equation. Let's figure out how these 2 tensions compare.
So where are we going to pivot?
Where do you want to put the pivot?
In the center.
In the center? Where mg is? Okay. I'll pick the center right there. If that's my pivot point, then the sum of my torques equals 0. How many torques? 2. I have a counterclockwise E1 here, and I have a clockwise E1 here. Or, if you're being very physics-like, you would say that these are positive torques, and these are negative torques, because the positive torques have vectors that point out of the board, and this has counterclockwise as vectors that point into the board. Okay? All right, so the torque for this one would be 5 times T1, right? Radius of 5 times T1. My angle is 90, so that disappears. And over here I've got 2.5 times T2. Therefore, T2 times T1 equals T2, or T2 is twice as big as T1.
Yay.
Okay? And you can plug that in up here and figure out exactly the size compared to mg then, right? One of them's going to be 2/3 mg, one's going to be 1/3 mg.
And you can say that they equal each other because the pivot points in the center.
We say that they're equal to each other. Torques are equal to each other because it's not
It's on.
accelerating. It's sitting still.
I think that rivals the fun,
Yes, I murder the English language every day,
It's
just for
okay.
fun.
You're a physics teacher.
That's right. I can't spell physics with an F, so these are all messed up for me.
Wow.
Okay, number 8, or number 9.
Number 8.
We did number 8. Number 9. All right, so here we go. We've got an mg and an mg. And then we've got a tension 1 and we've got a tension 2. All right, there you go, everybody. I want you to figure out for me, please, tension 1 and tension 2. Tell me what they are in terms of mg. Go. Sum of the forces in the x equals 0.
And the Y.
Okay, but that doesn't do us any good, right? Okay, the sum of the forces in the y equals 0. So therefore, T1 plus T2 equals 2mg. I'll give you that one.
Yay. Okay,
Yes.
and
But now the sum of the torques equals 0. You need to pick a convenient pivot point.
the center.
No, because of this.
You could pick the center.
Oh, so that's
Actually, you know what? There's
you pick the whole bar.
There's
you
4
could pick
places.
it here, you could pick it here, you could pick it here or here, and if you want to, you could pick it here. It doesn't matter. But here the math is harder, right?
Yes.
There are 2 spots where you could pick it where you'd have a single equation and a single unknown. Where are those 2 spots?
Where tension is.
Yeah, you could pick it here or here.
And
This is why that works.
and that just gives you tension.
Because now, this one produces no torque, so it disappears from the equation. T1 disappears. And so now my torques are, I've got a, what, a negative torque here, and a negative torque here, and I've got a positive torque here. And so these 2 negatives must equal that positive. So I end up with,
T2 equals 2mg.
that's right, the radius is 1, right? So I get T2, my radius is 1. But be careful, this radius is,
2.5.
ooh, wait a minute. How are you going to do this? Are you going to say this is broken up into 10 pieces so the radius is 10 here?
Yeah,
Yes.
10 T2.
Okay, let's go 10 T2 then.
Equals 2.5 mg. plus
2.5
5.
mg plus 5 mg, right? Everybody got that? Radius times force, radius times force. And the cosine theta, I'm sorry, the sine theta, sorry, is sine of 90 again. So what's that turn out to be? 10 T2 equals 7.5 mg. So T2 equals 0.75 mg.
And then my first equation.
All right, so if that's 0.75 mg, then what's T1? 1.25 mg equals T1, right? After plugging it back in. And there you go. And everything's right with the world. All the math comes out.
Yay.
And you see how this could easily escalate into something you probably don't want to do just for fun? Well, you might. I mean, this is actually kind of cool that you can work your way through. What we ended up doing was we had objects like this.
What are you doing?
He's making a spaghetti bridge.
Okay, so we have a bridge with 2 large cars on it, and we want to figure out
They're torquing.
how big do I have to make this piece right here so it won't break? So essentially, how big is the tension and or compression in it, and that'll tell you how big of a piece of metal you need to put there. And so you'd have to pull each one of these out, piece by piece, and write the torque. You'd have to write these 3 equations for each one of those.
Ooh.
What about the ones going like those 2? Right?
Exactly.
Ouch. Yes.
Now you know what? It's not that bad. What you end up with is a big honking matrix. And then once you figure out every equation, you put it in your matrix, and you hit solve,
Yes.
right?
It spits the answer.
And it spits the answer out. And there you go. It's not that bad. But what we did here was not that much more than what we're doing here. It's really not. I mean, there's a few new things you got to incorporate, but it's not that big a deal. So you're almost engineers. You're almost dangerous enough to build a bridge.
I would not trust anyone.
Yeah, you'd build it, but I don't want to drive it. All right.
Oh, that's true.
Okay, let's do our next one. All right, number 10. Okay, number 10. Will you please, in number 10, can you figure out how big the tension has to be and how big the forces at the wall have to be? The horizontal force and the vertical force. Can we figure those things out? Okay, this begins with a good free body diagram.
MG down.
We got mg down the center. We've got a tension this way. We have a...
Vertical up.
All right. First of all, everybody, can we figure it out? Vertical and horizontal force at the wall. Do we have to have a horizontal?
Yes.
Which way?
Right.
Okay, so it's got to be this way at the wall. You know what? I don't like drawing them like that because you lose them in the diagram. There's my horizontal. Do I have to have a vertical there?
Yes.
Yes. Which way does the vertical have to be?
Up. Up.
Does it have to be?
Up.
Is there a component of tension that's up?
Yes. Here's a way to figure out. Pick your pivot point right here. If you pick your pivot point right here, it can't rotate about that point. So this one doesn't produce any torque, right? Nor does this one. We have only one force producing a torque, which is this way. So therefore, I've got to have some other force here canceling out the counterclockwise torque of mg. So which way does that force have to be?
Up.
Okay, so we have to have a vertical force there. All right. Please write your three equations. The sum of the forces equals 0. The sum of the forces in the x equals 0. Sum of the forces in the y equals 0, and the torques equals 0. Write those out to see what they tell us. What does this equation tell us?
It equals 0.
H
There's no
equals
movement in the
TX.
x direction.
It tells us that this equals
T of x.
this, right? The x component here equals this.
Okay.
All right, what does this equation here tell us?
The vertical tension plus V
TV plus
Equals
V
mg.
equals mg.
T in the y direction, or TV, whichever you prefer, plus V equals mg. All right, so that's what we get there. We get that Tx equals h. All right, in the torque, where do you want to place your torque?
on the right.
MG.
On the right.
Right of the board, please.
You know what?
He said please.
You know, there are several places that you can place this. You can place it at the far right. If you place it at the far right, you eliminate tension and you eliminate the horizontal force. And you just have these two.
Okay.
I'm going to pick it in the middle. I'm going to show you a trick.
Yay.
You pick it in the middle. You still eliminate H. You eliminate mg. And of these two, Tx and Ty, which one produces torque?
TY.
Ty. You see the distance here? You see the distance here? They're the same? So what does that tell you about V and Ty?
They're equal.
They must be the same. So from this equation, we get that these two must be the same. Now look, since these two are the same,
So 2Ty equals MG.
that means that these are equal to mg over 2.
Yay.
All right? All right, now, you would have got that if you picked the pivot point at the right side as well. Okay, is this starting to make sense?
Yes.
It's better.
What's the third equation? Yeah, so what's the torque equation?
In this one, I picked it at the center, which meant that the radius, which was 5 from here to here, because each one of these is 10 long, 5 times Ty equals 5 times V, which means that Ty equals V. Okay? All right, here's number 11. Number 11 looks like this. You've got an mg over here. You've got an mg here. You've got a tension here. All right? At the pivot point, at the wall, do we have a horizontal force?
Yes.
Which way?
To the right.
Do we have a vertical force?
Well, yes, I think. Yes.
It is down. It is down.
It is down. That's what I got.
You're picking down.
Yes, because if you put your
Because I put a
Losers.
pivot in the center.
yeah, and then you
Not
get rid
too
of that
high.
whole middle thing. Then
I think you're losers.
Oh, we're this way.
no
Okay,
winners.
I actually think you're right.
Okay.
Okay, here we go.
He just thinks we're losers on top of
That's
that.
right. You just lose. Okay, this equals this, right? The sum of the forces in the x gives us these two are equal. Got it?
Yes.
Okay, the sum of the forces in the y doesn't really tell us if we have a vertical force here or not. So, let's do this. I picked my pivot point in the center because it eliminates T and mg and h. When I do that, does that tell us about what goes on here?
Yes.
Okay, because I'll have a torque from this one this way. No torque, no torque, no torque. I need something, or otherwise it's going to rotate. So therefore, I have to have a torque this way, or from here, this way. Which means that my force over here must be down.
Mr. Bird, on all the other problems, couldn't we have put V somewhere else, but make sure that it was bigger?
V somewhere else?
Yeah, the vertical force then. We wouldn't have to put it on the wall.
Oh, yeah. In theory, you could put that force anywhere, but since it was only attached to the wall, it would be at that spot.
Okay.
Okay, that's a good point. You can put it anywhere you want. Like, for instance, like this is here. I can put my vertical force anywhere along here and put it in equilibrium. The thing is that here, the vertical force that I'm pushing down with is easy. It's little because I have a big radius. As I put it in here, it becomes harder and harder because I have a tiny radius. So the vertical force has to get bigger and bigger. Okay? All right. All right, everybody. This force here, this vertical force, please determine how big that is.
MG. MG?
I'm gonna say
MG?
Yes.
Yeah, because it's really simple because since we did this torque right here, this torque has to equal this torque. They have the same radius, right? So therefore it has to equal mg. So therefore, how big is this vertical piece of the tension here then?
MG.
No.
No, wait.
Does it matter?
I'm asking.
It has to
Do it matter?
No, it matters.
Oh, wait, yeah. It has to equal 3 MG.
1, 2, 3. Oh, I'm sorry. From the torque equation, you're right. It makes no difference. I'm just asking how big is it?
Oh,
3 MG.
It'd be 3 mg, right?
Yeah.
Because the y equation tells us that, right? Whether it's rotating or not, that has to be 3 mg. All right. And since we don't know the angle, we cannot find specifically what t is. We don't know what the angle is. We just know that it's, what, 3 mg squared plus h squared square rooted, right? Which doesn't help us out a whole lot. Okay, now look at this one. Strange angle thing. Where we have an mg at the center,
yeah, I did this wrong.
and we have a tension here, and we got something going on here. There's something that goes on at the axis. Is it horizontal, vertical, or both?
Both.
Vertical.
Both. Both.
Why only vertical?
Because you only have forces in vertical.
Since we only have forces in vertical, they only need a force to be in vertical to put it in equilibrium. So it's going to be vertical. But will it be vertical up or down?
Down.
Up.
Down.
Up, down,
I
up,
don't
down,
know.
up,
If you
down.
put it in the middle, wouldn't it be up there?
Okay, pick a good place to put your pivot point. You want your pivot point here or here?
Center.
Okay, here. So this one torques it this way. So this one over here has to torque it which way?
The other way. Negative.
Oh, this way. right?
Don't you have a? Oh wait, never mind.
So it has to be upward, right?
Yeah.
Crazy.
Not crazy, just unusual, special.
Yeah, that's what my mom says too.
That's what my counselor says, right? I'm special. All right. Now, next thing, everybody. How does V compare to T?
My guess is that there's.
Do they have the same radius?
Yes.
Yes.
So they're the same,
Which means they're 1/2.
which means they're 1/2 mg.
That's
Ooh, the magical one.
All right, the magical one. Let's do number 14 first, then we'll do number 13.
We have 2 minutes.
Oh, dude. Let's do number 13. Here's number 13. Oh, look at that. Non-uniform bar.
What?
Ooh.
It's got little, it's wonky. Okay, we have an mg here.
He's making up words now.
I am not. It's all British.
Exactly.
Does that make it better, or
We just make up any word.
it makes them less made up?
Okay. First of all, tension, mg, mg.
Oh, Lord.
How do I know tension is this way?
That's where the string would go.
Because you can't push on a rope, right?
Which one are you doing?
This is number 13.
Oh, okay. I thought you said that.
I was going to do 14, but
Live.
all right, I lied. Okay, which way is the horizontal component?
To the left.
To the left. It has to be the left because it has to balance this.
Why on this one is it to the?
Because tension's to the right.
Oh, okay, because on 12 it was up, straight up.
Yes, got it.
Okay.
Excellent. Learning has occurred. Okay, what's our vertical one right here?
I'm gonna say up.
No, down. Just kidding. Hold on.
Okay, this is your homework assignment.
Oh, good. Thank you.
I want you to find what is the vertical.
Thank you.
I want you to find it in terms of mg. And then I want you to complete, oh yeah, and put your name on your homework and turn it in.
All of
I
you.
can't do my homework because I'm on the paper.
You get a 0 then.
Wait, what?